Hello everyone, and thanks again for joining us for this presentation. Today I'll be talking about 3D polygonal meshes and how they can help improve the discovery of new features in marine datasets, beyond just using traditional point clouds and grids. These point clouds can come from a variety of sources, such as photogrammetry, LiDAR, or multibeam. The main requirement is just having dense enough data to support the 3D reconstruction. We really started this work to investigate new methods for feature-preserving shape reconstruction and how a 3D mesh structure can best support this. The idea was to look at existing technologies and see what could be adapted and applied to new areas. Throughout the presentation, I'll talk a lot about shape reconstruction and how that goes hand in hand with the concept of 3D meshes. Going back a few years, this really started with customers pushing us to better support high-resolution meshes created in packages such as Agisoft and Pix4D. This data was primarily coming from aerial drones, usually for coastal and nearshore mapping, such as in this example. Working with this data gave us the first examples and ideas about the benefits of using high-resolution meshes. With advances in lighting and camera technology, this quickly expanded to underwater data, with structure for motion packages producing impressive high-resolution data sets. This really pushed us to consider the wider topic of shape reconstruction and how a 3D mesh improves this. Using a slightly different example, this impressive whale fall data was recorded as ROV video by the Ocean Exploration Trust on board the EV Nautilus, with a 3D mesh created by the Monterey Bay Aquarium Research Institute. To support these 3D meshes, we needed to adapt how we handled the data. Furthermore, in addition to viewing the data, users wanted to work with it in the same way that they're used to working with gridded surfaces. So this included things like applying color maps, measurement tools, and interactive profiling. Also, in a case you need to create 10 centimeter contours for a dead whale, we have been experimenting with mesh contouring tools as well. The next major step was adding the ability to create a 3D mesh directly in our software. This opens up the capability to create new meshes from structure from motion data, as well as now multibeam and LiDAR. For example, this technology is particularly well suited for analysis of vertical structures, such as this example of a mesh created from multibeam data. The ability to create meshes was first introduced in Fledermaus 8.0, and we've been focusing on improving it in each follow-up release. In addition to making the process faster and with higher quality output, one of the key areas we have focused on is making the creation process as easy as possible. With the latest release, it's now almost as simple as creating a grid with very few required parameters. This area I'll show a little bit in our demo later in the presentation. In terms of applications, this technology is useful really anywhere that shape reconstruction is important. This provides benefits for visual perception, quantified analysis, and the output of high resolution derived products. This can apply to safety and navigation, where proper identification of features is important, but especially in areas such as marine construction, salvage, asset inspection, as well as coastal planning and ROV and dive planning. These are all applications where you want the most understandable and accurate representation of your data when making decisions and plans. Now, you may be familiar with using meshes to represent geospatial data, as well as using TINs, which have been a common part of surveying for many decades. The real difference we are seeing now is a shift from reducing data to fit within hardware limitations to using as much data as possible for accurate shape reconstruction. This has been really enabled by three things. The first is the growth in CPU and GPU capacity, especially in regards to multi-core processing. The second is the advancement in shape reconstruction algorithms that allow this process to happen. And the third is the increasing availability of dense, high-precision point cloud data. This is coming from multibeam, LiDAR, as well as the structure for motion data sets. Before we go any further, I want to take a minute to talk about what is a mesh. If we look at this example, we can zoom in until we get down to the individual triangles that create the mesh. Each triangle is made up of a series of vertices, which are then connected by edges. Putting that together, we can form the face of the triangle. Now, when we put multiple vertices, edges, and faces together, we can represent objects such as this rabbit. Increasing the number of triangles gives us a more accurate representation of the shape. But it's important to note that because we can accurately model shapes with the 3D mesh, even if at the original lower resolution, I'll just step back to there, you could tell pretty easily it was a rabbit, and features such as the ears are still preserved separately from the body. Now, applying these concepts to a traditional multi-beam survey, we can start with this 10 centimeter grid of 4 rects. Comparing that to a 10 centimeter mesh, at this scale there's not a whole lot of differences as I move back and forth between the two. Looking at the grid, and then looking at the mesh. However, there's some interesting structure on this particular rec, which we can look at a little bit more closely. Looking at the grid, we can see some details, but then comparing it to the original point cloud, we can see that we're also missing details, as well as cropping some dimensions as the grid averages out all the points in each node. Now, moving towards the mesh, and comparing that to the point cloud, we can see a much better preservation of the shape, as well as preserving the full dimensions of the object. One challenge with mesh creation is that it can sometimes produce more detail than is necessary, beyond what the resolution of the data actually supports. We can see that in all the little fine details, almost the little bubbles across the surface. One thing we're experimenting with is our smoothing filters, which preserves the overall details, but then removes those fine, unnecessary details. Now that we have looked at some mesh examples, let's review some of the benefits, starting with variable resolution. When creating a mesh, you provide a minimum resolution, which is the smallest triangle area that is created. However, the creation algorithm will adapt the resolution as needed based on point density and the shape itself. Now, one of the most visible benefits of a mesh is the ability to model areas with overlapping Z values, such as sloped walls or protruding structures, such as this highlighted area. Lastly, mesh creation also reduces the data volume while still preserving shapes and structures. In this example that we've been working with, the original point cloud data had just under 8 million points, but our mesh was able to reduce that to 2.5 million vertices while also helping to improve the visual analysis. Putting that all together, let's do a quick comparison of grids and a 3D mesh. For grids, they're quick to build, and also the concept is easy to understand. Everyone can kind of understand the concept of creating a bucket, throwing in some points, and doing a simple algorithm like shoal biased or averaging. But the downside is that a grid is limited as a 2.5D surface, which means that it can only represent one Z value or one depth for each grid cell. So this prevents us from accurately representing quickly changing slopes, overhangs, or any protruding surfaces. Comparing that to a mesh, the build times can potentially be slower as you increase resolution. Also, the concept can be a bit more complex in terms of how the shape reconstruction algorithms work. But the benefit is really the ability to handle true 3D surfaces of all shapes and structures. Now, kind of in between, bridging somewhat some of the benefits of both, we have variable resolution grids. These can address some of the limitations of a standard grid, but ultimately are still limited to being a 2.5D surface and still cannot accurately represent certain shapes, such as concave slopes and overhangs. Doing a similar comparison for point clouds, we can see that points have the advantage that there is no additional building time compared to grids and meshes. As your point density and resolution increases, mesh construction can be resource intensive. However, a modern multi-core machine can help offset this. Points also naturally are representing data at the full resolution, with 3D meshes usually coming close to the same. One of the potential downsides of point clouds is that you are working with a large amount of data, whereas mesh can help reduce the volume. Point clouds are also not a connected shape, which complicates quantified analysis such as slope or volume calculations. And finally, point clouds can be challenging for visual perception, as you are either seeing too many points at once or obstructing fine details. There are, however, some advanced point shading techniques that can be used to improve the visual perception with point clouds. One of these point shading techniques is eye-dome lighting. For example, if we start with a point cloud, you can see a lot of details, but you're also seeing too many points as you're seeing through the point cloud onto the far side. If we're applying a point shading technique, such as eye-dome lighting, we've really greatly improved the visual perception capability. Going further and using a 3D mesh, we can see that fine details that were obscured with even the eye-dome lighting techniques are now visible. Furthermore, by having a complete and constructed shape, we can then do additional analysis such as density or volume calculations. So does this mean we should always use meshes instead of points? The answer really is no. The best approach is using a combination of data structures to best fit the situation in your data. For example, a simple first application for a mesh can be to directly combine it with point clouds to help create structure and include points on the backside of the cloud, as we can see in this example. This can be further illustrated with a multi-sensor survey, such as this data set from Bibi Hydromap. It is a combination of a T20 multibeam, a Blueview scanning sonar, and a Carlson Merlin laser scanner. I've also added some airborne LiDAR, which I gridded as a surface to add overall context. Now if we zoom into one of the bridges, the best choice is to represent the bathymetry using a regular grid. But for the bridge itself, we can replace the aerial LiDAR grid with a mesh combining the laser scanner, the scanning sonar, and the aerial LiDAR points. We can then also add the laser scanning data for the riverbank. But as this is mostly vegetation, it really just works best as a point cloud. Moving to another bridge along the river, we can again see the benefits of having a mesh representation for the combined data. Now, although we have been working with the bathymetry as a grid, it is also useful to examine areas of interest and to dynamically mesh those areas. In this example, we can select an area and create a high-resolution mesh. This improves feature discovery and analysis, and in this case, we can better identify and measure this car upside down on the riverbed. To summarize what we've been learning about 3D meshes so far, they're really great for accurate shape reconstruction and discovery of new features. However, they're not a magic bullet. They have some pros and cons, specifically in terms of some of the resources, hardware resources needed to construct them. So really, the optimal solution we should be looking at is working dynamically with multiple data structures. This depends a lot on your data, what you're doing with it, and it can progress during different stages of your projects. So looking at points, grids, and meshes as we've done today, but really looking beyond that to kind of a wider range of file formats. That's one thing that Fledermaus has always been built upon, is a wide range of objects, both very specific ones coming directly from Quincy and Chimera, as well as more generic formats that can be used to take data from all kinds of other different packages. And it's really the ability to bring this all together in a single 4D environment that you really get the advantage of moving back and forth between these data structures. Before I get to the demo, I would like to talk a little bit about what has been new in Fledermaus 8.0 leading up to our 8.2 release coming up shortly. Really from the beginning, we wanted to clean up the user interface, address a lot of the areas that people had struggled with in the older software. So that was why we created an optimized user interface, as well as updating the 3D engine to allow for new things like the high-resolution 3D meshes. We also looked at some of the key foundational things that people use Fledermaus for and try to make that better. One of those was presentations in movies. So Fledermaus 8 has a built-in presentation system. We already talked about the high-resolution meshes. And also, I skipped over one there, was the profiling. A key part of what a lot of people use in the software is interactive profiling. So we really enhanced that for features, interactive ability, as well as being able to work with a lot better with multiple surfaces. And lastly, we've added the QPS project support. Now this allows you to move seamlessly really between each of the different products. Between Quincy, Chimera, and Fledermaus, depending on what stage and what work you're needing to do. At this point, I'm going to step out of PowerPoint and launch Fledermaus and do some examples directly of what we're talking about and some of the other features. So starting off, I have the project open dialog. Now, as I talked about, this is a common project structure used across all our applications now. The one I'm going to work with is the last project I was using. So I'm going to open that up. Now in Fledermaus, when you open a project, by default, if you don't have a scene already, you won't see anything. On my right, I have all the files that I can import or start viewing directly in Fledermaus. So in this case, I'm going to choose a selection, and I'm going to add those into the scene. One thing that if you're a Fledermaus 7 user, you're used to scenes being the main structure within the application. In Fledermaus 8, you have both projects, which are optional, but then you still continue to have a scene. You can have a project with multiple scenes, or you can just work with a single one for each project. Now with this data, I'm going to select, and I'm just going to turn off the points for a second. Each of these QPD files I can choose to show as a track line, or I can turn on the points as part of this data set. To help with my organization, I'm just going to highlight all of these files, or these lines, and I'm going to create a group. This will make it a little bit easier in terms of turning things off and on when I want to do that. One thing that is new within Fledermaus 8 is the ability to multi-select files. In this case, all these QPDs, I can turn off and on the points, or turn off and off the track lines for this data set. Now this is a very interesting data set. As you can see, we have a number of tanks with a fair bit of detail that we can see. This data is collected with an R2 Sonic 2024 operating in the ultra high resolution or 700 kilohertz mode. Data was collected in Quincy with data processing done in Processing Manager and then into Chimera. Now this area is known as St. Pete Beach Reef. It's an artificial reef off of St. Pete Beach, Florida. And because it is an artificial reef, it has been surveyed before. So I'm going to load some additional data from a previous survey to add what we're working with now. Once the data is loaded, we'll be able to do a comparison between the new point cloud data and the older data set. I'll just zoom back here a little bit, and we see the overall area. There's quite a number of tanks. There's a barge structure as well that was sunken, all for the creation of this artificial reef. For now, I'm going to turn off the points. And one thing I noticed that my track lines are below, as well as my point data is not quite lining up. So I'm just going to pause for a moment. Normally in this situation I would go into Chimera, address my issue, and then import the data again with the issue corrected. In this case I can kind of simulate that. I didn't actually have to go into Chimera. I have it already fixed up with some process point files. Now that my data is loaded, I'm just going to turn off the other, and then I have the corrected data lining up quite nicely with the older data set. I'm just going to select both, use the comparison flicker mode, just comparing between the older data, which is gridded, and the new point cloud data. And we'll look a little bit more. But I also want to add a little bit more context to what I'm looking at. So I'm going to add an additional regional data set. Now I'm really going to zoom back and take a look at this new data set that I've added. So this is the St. Petersburg, Florida area, Tampa Bay, and then we can zoom into the area where we have our data. So we can see we have now a couple different levels of resolution, going from the relatively lower resolution joint topobathy LiDAR down to our older survey, and then getting all the way to our new high resolution survey. One last thing I want to add to this data set is a chart, so I'm just going to add that as well. So now we can see kind of the area that we're looking at. Because it is an artificial reef, it is marked on the chart as a fish haven. And let me just grab my chart, and I'm just going to adjust my transparency here so we can kind of see the areas that we're talking about and how that lines up with the chart. Now if I turn on my overall area, I find this can give you a decent kind of perspective on our survey area that we're looking at, as well as the combination of the topographic LiDAR with the combined bathy. At this point, I'm going to create a space-time note, which is a marker that I can place for the view that I want to save here for what I'm going to be doing in a minute in terms of creating a presentation. If I look at our overall area, I'm just going to create that as my view. I'm going to move down closer, and I apologize, everyone's bandwidth is probably a little limited these days, so I'll try to do this, move around a little bit slowly, as the frame rates are probably going to be a bit low over the internet these days. So looking at this area, I'm going to turn off the chart as I get in closer, as well as the reference areas, and kind of take a look at this area. What I'm going to want to do at this point is create a mesh, kind of a lower resolution mesh for the entire area. I'm going to create also a new space-time note recording the view for here for when I get to my presentation later on. So I'm going to select the QPD for the new data. I'll open up my create mesh dialog. The main thing you have to consider with the create mesh is the minimum resolution. As I talked about, it is variable resolution, so this is simply the smallest resolution. Some areas, if they don't need to be at this level, will be won't be as fine. But I'm going to put that, let's say, about 10 centimeters. Also, the next step is doing your samples per node. This is basically how precise or clean you feel your data is. So if you have very clean data, you would put that around a 1 or 2. If it's noisier or a little less precise data, you would get a little further up in 10 up to a maximum of kind of around 20. But this is very clean, very precise data, so I'm going to put that down at 1. Also, the radius search and density search radius, these will automatically be set based on your minimum resolution. So in most cases, you don't need to worry about what those values are set to. Usually I like to name this, and so this is my meshes, just to keep track of what parameters I'm using. So I'm just going to do that as an overview 10 centimeter mesh, as well as samples per node of 1. So I'm going to start that mesh creation process. Now that my mesh has completed, we get some statistics on how much memory was used and the amount of CPU usage or time for that creation. So I click that, it will load the mesh, and I'm just going to turn off points. Now the first thing is the color map needs to be adjusted, so I'm just going to open up my color map, clamp my range to the actual data, something that we should probably do automatically. Now I can take a closer look at this data set and really see some of the fine details. Again, this was a kind of a low resolution overview based on what this data can support, but we're still getting a lot of impressive detail. in these tank structures. As mentioned, this was all purposely sunk as an artificial reef. These tanks are perfect for fish habitat, and it's a very popular location for fishing. The next step I would like to do is create an actual interactive presentation. So I'm going to find one of these tanks. Let's pick this one here, I think. I'm going to add an additional space-time note there. Let's pick a good view for that. I'll record that view. What I can do now is just highlight those space-time notes, and I'm going to use the Add to Presentation option to add those directly to a presentation that I'm now going to start building up. One thing in Fledermaus 8, it has a very PowerPoint style presentation system. You have slides, you can build them up, progress through them, have transitions and actions on each slide. The big difference is it's all part of a geospatial system, and each slide is tied to a space-time node. So a space-time node is recording both an X, Y, and Z location, a viewpoint for the camera, as well as the time that you place that space-time node. You also have the ability to add specific notes or labels tied to each of those, similar to an event. So to preview, I'm just going to click on each of my slides. My first one was that big overview. I had turned off my overview data, so I'm just going to turn that back on. Then I have a little transition in and looking at the overall slides, and then going into that final kind of close-up view. So now I'm going to start the presentation. Similar to PowerPoint, when I launch it, it goes into a full screen mode. I've also added a logo as part of my project defaults. So now I can use my standard kind of advanced options to advance through each part of that presentation. So that's all right, but there's a couple of things that I want to do with that a little bit more. The first thing, I want to add a little content to that first slide. So I'm going to add to our content editor. I'm going to go with the template for kind of a title and subtitle. I'm just going to grab some text here, make sure I spell everything correctly. So I'm going to add a title and a subtitle. In addition, I like to make that transition from slide 1 to 2 a bit longer. So we're doing an interpolation in. So looking at the transition area, and I want to increase that to say 8 seconds, so we're not just popping in there so quickly. So it's good to be able to just kind of each time you make a change, bring it up, preview what you're seeing. So I can now see the title that I've added. I can now advance. I'm doing this all with a manual advancing. There's also a timed advancing, so each of those times would happen automatically. Okay, so that's kind of what I'm looking for. But when I'm zoomed in, my lower resolution data is kind of getting in the way. So going to slide 2, I'm going to go to my transparency slider, and I'm going to add a transparency override for that lower resolution data. I want to be completely hidden at the point, so making that 100% transparent. Okay, let's just do a quick test on that. Starting my presentation again, zooming in. Now as we're doing that 8-second transition, you can see that lower resolution overview area is fading away, and so once I get to my high resolution data, I only see that data. Alright, the next thing I want to do is when I get to my third slide, I like to automatically do an orbit rather than just staying there. So I'm going to adjust my transition time for that one. And I look at my on-slide options. I'm going to go to orbit. I'd like to do a kind of a slow, just kind of look at the detail kind of turn here. So I'm going to do a clockwise slow turn, and let's take a look at that. Okay, this is my second slide. Moving into the third, it's automatically kind of going to come in. Also, it's faded back the lower resolution data because I forgot to add a transparency on the third slide. But in this case, it's kind of doing what I want, kind of doing a little beauty shot, a little slow turn around the data that I want to do. But before I forget, I'll add a transparency for that data on that last slide. The next thing I want to do as part of my presentation, I just want to add an image to my last slide there. Now I want to do it after a little bit of rotation, so what I'm going to do is duplicate that last slide so we're at the same location. Again, because it duplicated, I also get the transparency override. Now I'm going to go into the content editor. In this case, I just want to put a centered image, just to add a little context or to be able to, as part of my presentation. I have an image prepared here. Okay, and then let's play our presentation again. Okay, our titles are a little slow pan in. If I get bored, I can always jump ahead, skip directly to the slide I want. Transition to the orbiting slide. It comes in and it's doing the orbiting. And if I want to add that image, I advance to the next slide and I have located that directly. Now you can move that to the side. You could do a different comparison depending on how you want to add that into your presentation. Once you're finished creating your presentation, you have a couple different options of what you can do with it. You could take each slide and just export that directly as an image. You could package up the scene and distribute that with the Fledermaus Free Viewer. It used to be called iView 4D. We've rebranded that as the Fledermaus Free Viewer. With the Free Viewer, you can open up the scene, which has the presentation contained in it, so you could pass that on to someone and they could play it and advance it as you constructed it. In addition, the movie making system in Fledermaus 8 is now completely based on the presentation system. So you're setting your timings for your transitions, you're setting what happens at each location. You don't have to worry about editing flight paths. All the flight path is done automatically for you. So then I can render my presentation as a movie. I have choice of how I want to encode it, going from HD all the way up to an 8K resolution movie. I can adjust my frame rates from standard all the way up to ultra high frame rates, and then I can start the rendering process as an output, standalone output, an MPEG file that you can distribute of your presentation. One of the nice things of having this all in the structure as opposed to exporting it and working with it in a video editing or directly in PowerPoint is if, say, your boss comes along and says, I like your presentation, but you know what, I really want some more resolution on that close-up. Well, at this point, we can go in, we can make those changes directly in the presentation, and we still can keep the structure and everything that we've created. So I'm just turning my point data back on. I'm going to highlight the area that I want. Oh, kind of the wrong angle here. Let's just get a top-down view. Okay, just going to select the area that I'd like to create my higher resolution mesh. Select my source point file, bring up my mesh dialog. In this case, I want to go with a 2 centimeter mesh. I'm just gonna, and again, same samples per node. I want to crop it a little larger than the 2 centimeters, so just I'm going to adjust and put my density search radius at 8 centimeters. So I want to label this correctly, tank 3, 2 centimeters. And S1 DR8. Okay, I'll begin that meshing process. Okay, because that's a relatively smaller area, even though it's at the higher resolution, the mesh creation time was not very long. Okay. And now we can take a look really edit that data, I'm going to turn off the markers for my space-time notes. Again, turn off my base thing. Really can see how impressive that data is, and when we're getting down at that 2 centimeter level. Also, a new feature that we have with meshes, I'll just bring that up, is our mesh slicing capability. So with that, you can adjust in X, Y, and Z and slice through the mesh. So in this case, I can go up and Z if I want to remove areas there, or if I kind of want to take a kind of a slice through it in that direction. I'll just move my slice control over here, and I can kind of take a look. Kind of helps you do some analysis by being able to directly slice through that that mesh that you've created. Now I'm just going to bring that back where I have it, and then turn on my overview mesh. So in this case, now I'm going to go, as I said, I wanted to improve this for my presentation. I can start that up again. Oh, sorry, I forgot to turn on my overview scene. So now I've started my presentation. I'm just going to skip the titles, skip ahead. Now I can see that I have my higher resolution data. But well, that doesn't look great because I have the overlapping between the high and low, but we know how we can solve that. I'm also going to clear my selection. Just zoom in. I don't need my selection box anymore, so I'll just clear that. And again, going to my third slide, I want to add a transparency override for my overview mesh. Let's bring that down. And one last time, let's just take a look at our presentation. Okay, we have our titles. Kind of a zoom in, skip ahead. I can zoom here. I do my transition into the high resolution area, and then I have my kind of beauty shot of my 2 centimeter mesh. As I said, I can now package that up, have someone else use that without having to have a license. I could make a movie, or I could do individual data exports of what I've created. Okay, so that's kind of what I wanted to cover for this quick little Fledermaus demo. If anybody would like to look into anything in more detail, have any questions about certain areas, please let us know. We're happy to set up demos and talk to you about anything that I've shown today. Just going to go back into my presentation. And again, I'd like to thank two of the sources of the data that I used in that demo, that high resolution data from R2 Sonic, as well as the original artificial reef data from the University of Southern Florida. So before I kind of finish up and hand things back to Matt, I just want to talk about what's coming up in Fledermaus 8.2. This is a release that's just around the corner. Now, one of the things that's nice about our upcoming releases is that we'll be adding the Linux and Mac versions. These have not yet been available for Fledermaus 8. We've had them for Fledermaus 7 for many years, so we'll be adding it for this release. Another thing is we've improved how you're working with scenes. So it's an easier way to go from a project, all your individual things that you add to a scene, then you have the ability to encapsulate that, a share scene that bundles it all together, compresses it in an easy way to distribute that to another QPS user or directly to someone using a free viewer, the Fledermaus free viewer. Also, we have a number of incremental upgrades, as I've kind of highlighted the easier mesh construction. Our core surface, which is using the Grid 5 structure, has been updated. We're continuously improving our geodetics, as well as there's been a number of optimizations for the video playback, something that I didn't talk about today, but the ability to take full motion video, combine that with a track line, a time reference, and play that back in your scene as well. So thank you everyone for listening. Hopefully there was something useful, and like I say, let me know if any questions. So at this point, I'm going to hand this back to Matt to finish things up.